concept of cardinality is an important idea to foster in the younger grades, so we're going to take some time to understand this particular topic in this lesson. Take a look at the following three sets. What do you notice? You may have noticed that the first two sets look similar, the only difference being the order of the elements A, B, and C. The third set is also similar in the sense that it only contains the elements A, B, and C, but B has been written twice. When dealing with sets, we often don't care about the order of the elements, so that the first two sets, ABC and ACB, are actually the same. Also, we typically only write each element once, so the third set could really be written like this. And that means that it's really similar to our first two sets. For this kind of relationship where each element of one set is also found in another set, we use the word equal, and we can use the equal sign that we know. In our case, we can write A is equal to B is equal to C. All sets are equal. If you can think of any other sets that are equal to A, B, and C, feel free to share them in the comments below. Take a look at the following three sets. What do you notice in this case? You may have noticed that the first two sets, A and B, have 3 elements each, but the third set has 4 elements. There is an important idea mixed in here. Sets A and B share the same number of elements, so we might want a way to be able to write this mathematically. For this kind of relationship, where two sets share the same number of elements, we use the word equivalent. In our case, we can write A is equivalent to B. In this case, we also have A is not equivalent to C, and B is not equivalent to C as well, since they don't share the same number of elements. Now suppose we had a fourth set here, D, where I'm just going to switch the order of our letters, so we have B, A, C. Now we could write A is equal to D, and we could write that A is equivalent to D because they share the same number of elements. However, mathematicians tend to prefer the use of the equal sign here over the equivalent sign. And that's because the equal sign carries a bit more information. The equal sign is going to tell us that we know they have the same number of elements and that the elements are actually the same. If you can think of any other sets that are equivalent to A and B, feel free to share them in the comments below. Since it might be useful to talk about how many elements there are in a set, we're going to define a new concept on this slide. We're going to use the word cardinality to refer to the number of elements in a set. Now, there are a few different notations to be aware of, the most common being vertical bars, similar to our absolute value signs. Another common notation that you might see is the use of a small letter n with your set in brackets. Let's take a look at this set, and let's call it A. How many elements are in A? Well, we could actually physically count them, 1, 2, 3, 4. So we could use our two different notations. We could use our vertical bars to represent the cardinality, and I could say there are 4 elements inside of set A. We could also use our little n notation, like this. This also means cardinality, or how many things are inside of set A, and we could write n of A is equal to 4. What about set B here? How many elements are inside of set B? Well, in this case, if we want to use the vertical bar notation, we could say that the number of elements inside of B is 10. And again, we can just count these. Using our other notation for cardinality, we could say the cardinality of set B is equal to 10. take a moment to pause the video now and try to determine the cardinality of the sets C and D. Alright, let's take a look at how you did. For set C, it might be helpful here to actually go through and list our prime numbers up to the number 25. So starting with 2, we have 2, 3, 5, 7. 9 isn't prime, it's divisible by 3, so 11 is our next prime number, followed by 13. 15 isn't, but 17 is. And then I think there's just 2 more, 19, 21 isn't prime, 23 is, and 25 is not prime. So here is our list, and we could go through and count the numbers inside of this list. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we could say that the cardinality of set C is 9. So for set D here, it might be useful to change from our set builder notation, which is what we have now, to a list. So what we need to do is pick whole numbers x that are between 0 and 5, and we're going to square them. So the number 1 is between 0 and 5, and 1 squared is equal to 1. 2 is our next whole number, and 2 squared is equal to 4. 3 would be our next whole number, 3 squared is 9. And then 4 is our last whole number in between 0 and 5, and 4 squared is 16. So here is our list of elements that are inside of set D. So we know that the cardinality of set D must be 4. Finally, let's take a look at a few different cases. Recall that the empty set can be written in 2 ways, either with a 0 with a slash through it, or as an empty ordered list, so our squiggly brackets, and we just don't put any elements inside. What do you think the cardinality of the empty set is? Well, does it make sense intuitively that the cardinality of the empty set should be 0? That's because there are no elements inside of this set. Another weird case that might happen is we have a really large set that actually contains an infinite amount of objects, like our natural numbers here, 1, 2, 3, 4, and so on and so on. In this case, we say that the cardinality of this set is infinite. Something that I find super interesting is that there are actually different sizes of infinite sets. This means that some infinities are bigger than other infinities, Hazel Grace. Maybe a bit more on this later. All right, my little epsilons, stay positive.